At 9:47 a.m. on October 14, 1943, at an altitude of 27,800 feet above Schweinfurt, Germany, a Boeing B17G Flying Fortress, identified by its crew as Pennsylvania Steel, held its assigned position in C. A tightly packed American bomber formation. Air outside the aircraft measured -48 degrees Fahrenheit. At that temperature, exposed metal became brittle, lubricants thickened, and human survival depended entirely on oxygen systems and insulated flight clothing. Inside the cockpit, First Lieutenant James Robert Callahan sat in the left seat, his hands resting on the control yoke, his oxygen mask delivering short, mechanical breaths with every inhale. Callahan was 24 years old. He had completed 11 combat missions. Statistically, that meant he was already living on borrowed time. Outside his cockpit window, 281 American bombers stretched across nearly 40 miles of sky. They flew in rigid combat box formations designed to concentrate defensive firepower, unreduced individual vulnerability. No aircraft could maneuver independently. Every heading change, every altitude adjustment, every power setting was coordinated. Below them lay Schweinfurt's ball bearing factories. These industrial complexes produced the majority of Germany's precision bearings. Bearings used in tank transmissions, bearings used in aircraft engines, bearings used in submarine propulsion systems. Without them, Germany's ability to wage mechanized war would degrade rapidly. This was the second raid on Schweinfurt in 3 months. The first had cost 60 bombers. Every man aboard Pennsylvania Steel understood the numbers. 1 out of every 4 B-17s that entered this airspace did not return. The aircraft carried 4,000 pounds of bombs in its open bay. Its fuel tanks held approximately 200 gallons of high-octane aviation gasoline. Its structure, control surfaces, and engines were functioning as designed. At least, they were at 9:47 a.m. 4 minutes later, at 9:51 a.m., German anti-aircraft batteries opened fire. 88mm shells detonated throughout the formation, each explosion sending steel fragments outward at velocities exceeding 6,000 feet per second. Shock waves rippled through the bomber. Aluminum skin flexed and rang under impact. Callahan held the aircraft level. Breaking formation was not an option. Isolated bombers survived an average of 11 minutes against concentrated fighter attack. The manuals were explicit. Survival depended on discipline, not reaction. At 9:53 a.m., German fighters arrived. Focke-Wulf 190s approached in coordinated attack groups. These were not probing passes. They were close-range assaults flown by heavily armored aircraft, using Sturm tactics. Each fighter carried multiple 20mm cannons and heavy machine guns. At a convergence distance of 200 yards, their combined firepower could disintegrate a bomber in seconds. Callahan watched a bomber 3 positions ahead absorb a direct hit through its cockpit. The nose section vanished in a burst of aluminum and glass. The aircraft rolled inverted and began its descent toward the ground. Debris followed it down. There was no commentary over the intercom. No one reacted. The formation continued its bomb run. At 9:54 a.m., Pennsylvania Steel released its bomb load. The aircraft rose slightly as 4,000 pounds dropped free. Below, Schweinfurt disappeared beneath expanding clouds of smoke and fire. The formation began its turn toward home. 2 minutes later, at 9:56 a.m., a single German fighter broke from above and behind. The aircraft was equipped with air-to-air rockets designed specifically to break bomber formations. The first rocket detonated above Pennsylvania Steel. The second struck the aircraft's tail with the force of 90 pounds of high explosive, the entire tail assembly separated instantly. The vertical stabilizer, the horizontal stabilizers, the rudder, the elevators. All gone. At 9:57 a.m., James Callahan was flying an aircraft that should not have been capable of controlled flight. The control yoke went slack in his hands. There was no resistance, no feedback. The nose dropped. The aircraft rolled slowly to the right. According to aerodynamic theory and every flight training manual in existence at the time, a conventional aircraft without stabilizing surfaces cannot remain controllable. The tail provides pitch stability. It counteracts the nose-heavy tendency created by engines mounted forward of the center of gravity. It also provides directional stability, keeping the aircraft aligned with its direction of travel. Without these surfaces, an aircraft should enter an unrecoverable spin within seconds. Pennsylvania still did not spin. It descended, slowly, unevenly, still generating lift. Inside the fuselage, the crew began reporting damage. The tail gunner's position no longer existed. Control cables had been severed. The rear of the aircraft was open to the slipstream, exposing internal structure to 180-mile-per-hour airflow. 8 men remained aboard. 1 was already dead. The aircraft fell out of formation. The remaining bombers climbed away towards safer altitude, leaving Pennsylvania still alone over central Germany. The immediate problem was simple and absolute. Without elevators or rudder, conventional flight was impossible. Altitude control did not exist. Directional control did not exist. Every principle of stable aircraft design had been violated. Yet the bomber remained airborne. What followed would not be flight in the conventional sense. It would be something closer to controlled descent, managed minute by minute using systems never intended to replace lost aerodynamic surfaces, according to engineering doctrine. This should not have worked. That it did would require explanation, according to the aerodynamic and engineering doctrine of the early 1940s. What was happening to Pennsylvania still should not have been survivable. A Boeing B17 was designed around a conventional SDA ability layout. Its 4 engines were mounted forward of the aircraft's center of gravity. This configuration made the aircraft naturally nose-heavy. That nose-heavy tendency was not a flaw. It was intentional. It allowed the bomber to recover from disturbances and maintain steady flight as long as its tail surfaces remained intact. The horizontal stabilizers at the rear of the aircraft generated a constant downward force. That force balanced the weight of the engines and the forward fuselage. The elevators, attached to those stabilizers, allowed the pilot to change pitch, climb, descend, rest or dive. The vertical stabilizer and rudder served a different but equally critical function. They provided directional stability. Without them, an aircraft could not resist yaw. Any imbalance in thrust, airflow, or damage would cause the nose to swing uncontrollably. Every training manual stated the same principle. Remove the tail from a conventional aircraft, and controlled flight ends almost immediately. Wind tunnel data supported this conclusion. Without stabilizing surfaces, airflow over the wings becomes asymmetrical. The aircraft begins to yaw. Yaw induces roll. Roll increases angle of attack on one wing while reducing it on the other. A stall follows. Once stalled, recovery is impossible without functional control surfaces. This process usually unfolds in seconds. Yet Pennsylvania still did not stall. The explanation begins with mass and momentum. At the moment the tail was severed, the aircraft had just released its bomb load. 4,000 pounds of ordnance had been carried in the forward bomb bay. When that weight dropped free, the aircraft's center of gravity shifted aft. Not dramatically, but measurably. At the same time, the tail assembly itself, which accounted for a significant portion of rearward mass, was gone entirely. The net result was a center of gravity that moved closer to the wing's aerodynamic center. This was not an ideal configuration. It was marginal, but it was closer to neutral balance than the aircraft would normally experience in combat. There was another factor. Before the bomb run, Pennsylvania Steel's trim tabs had been set for level flight. Trim tabs are small adjustable surfaces designed to reduce control forces. They apply a steady bias so that a pilot does not need to hold constant pressure on the controls. When the elevators were torn away, the trim tabs remained in their last position. That position produced a slight nose-up moment. Under normal conditions, this effect would be negligible. Without elevators, it became critical. The aircraft was not stable. It was barely balanced. The wings themselves remained intact. Each wing generated lift independently. As long as lift exceeded weight, the aircraft would remain airborne. What it could not do was maneuver in any conventional sense. Pitch control no longer came from elevators. It came from engine power. Increasing power increased airflow over the wings. That airflow increased lift, causing the nose to rise slightly. Reducing power had the opposite effect. It allowed gravity to assert itself and the nose to drop. Your control came from asymmetric thrust. By advancing engines on one wing while reducing power on the opposite wing, the crew could induce a slow turn. This technique was taught only as an emergency measure for minor control failures. It was never intended to replace an entire tail assembly. The limitations were severe. The aircraft descended at approximately 300 feet per minute. This was not a glide. It was a controlled loss of altitude at their initial height. This gave the crew less than an hour before reaching altitudes where German fighters operated most effectively. Wind compounded the problem. At 25,000 feet, wind speeds exceeded 80 knots. Without a rudder, the aircraft drifted sideways with the wind. Every minute, it moved farther off course. Structural stress added another danger. Without a tail, airflow separated violently at the rear of the fuselage. Turbulence battered exposed stringers and control cables. The aircraft vibrated continuously. Any additional structural failure could have caused catastrophic breakup. Engine reliability also became critical. Each Writer 1820 engine produced approximately 1200 horsepower. Losing one engine was survivable under normal conditions. Losing two would have made asymmetric thrust unmanageable. Losing three would have ended any remaining control. Fuel consumption increased sharply. Because throttle changes were being used for control, the engines operated outside efficient cruise settings. This increased fuel burn by roughly 30%. The margin for error narrowed with every passing minute. From an engineering standpoint, the situation violated multiple assumptions simultaneously. The aircraft lacked stabilizing surfaces. It relied on engine power for attitude control. Its structure was compromised. Its fuel consumption exceeded planned limits. Its descent rate was constant and unavoidable. No flight manual contained procedures for this scenario. The aircraft was not flying in the way it had been designed to fly. It was obeying physics in a narrow band where balance, thrust, and lift happened to align just enough to delay collapse. This alignment could not be maintained indefinitely. Every calculation pointed to the same conclusion. Pennsylvania Steel could remain airborne only as long as nothing else went wrong. In combat, that condition rarely holds. James Robert Callahan did not come to the cockpit of a B-17 as a test pilot or an engineer. He arrived there the same way most American bomber pilots did in 1943, through a system designed to produce large numbers of competent airmen quickly. Not Specialist Cullen was 24 years old on October 14, 1943. He had completed 11 combat missions, statistically, that placed him well below the average number required to survive a full tour. He was young, but not inexperienced. By the standards of the 8th Air Force, he was already a veteran. Before the war, Callahan's life had been ordinary. He came from Altoona, Pennsylvania, an industrial railroad town defined by steel, coal, and schedules. His civilian background was not aviation. Like many young men of his generation, his early adulthood involved steady work, routine responsibility, and little exposure to risk beyond factory machinery and rail yards. When the United States entered the war, the Army Air Forces expanded at a pace never before attempted. Callahan entered flight training as part of that expansion. The system emphasized standardization. Every pilot learned the same procedures, the same emergency checklists, the same assumptions about how aircraft behaved when damaged. Those assumptions did not include the complete loss of a tail section. Callahan learned to fly in trainers, then twin-engine aircraft, and finally four-engine bombers. By the time he reached the B-17, his training focused on formation discipline, instrument flying, and crew coordination. Individual flying skill mattered less than the ability to hold position precisely under stress. The B-17 was not flown alone. It was flown as part of a crew. In the right seat sat First Lieutenant Marcus Antonio DeLucci, 23 years old. DeLucci was Callahan's co-pilot. His responsibilities included engine management, checklist execution, and sharing control during high workload phases of flight. Like Callahan, he had completed multiple combat missions. Like Callahan, his training assumed intact control surfaces and predictable aircraft behavior. Behind them stood Staff Sergeant Eugene Lawrence Mitchell, the flight engineer. At 23 years old, Mitchell was responsible for monitoring engine performance, fuel systems, electrical loads, and mechanical failures. He was trained to diagnose problems quickly and apply standard fixes. His manuals described fuel imbalances, oil pressure loss, and engine fires. They did not describe flying without a tail. In the nose of the aircraft lay Second Lieutenant William Francis Hendricks, 25 years old, the bombardier. His primary task was precision bombing using the Norden bomb sight. On this mission, that task had already been completed. What remained was survival. Next to him worked Second Lieutenant Thomas Edward Sullivan, 23 years old, the navigator. Sullivan's job was to plot position, calculate headings, and estimate drift based on wind and airspeed. His training assumed a stable aircraft capable of maintaining altitude and heading. Neither condition existed after 9:57, a.m. in the top turret sat Staff Sergeant Donald James Pritchard, 24 years old. He manned twin .50 caliber machine guns and coordinated defensive fire against attacking fighters. His position gave him visibility, but also isolation. He relied on intercom communication and discipline to remain effective. Below the fuselage had been Staff Sergeant Robert Vincent Castellano, 25 years old, the ball turret gunner. His position was the most physically confined in the aircraft. Under normal conditions, exiting the ball turret required coordination and time. Under combat conditions, it became a liability. At the waist position stood Staff Sergeant Charles Henry Brennan, 26 years old, and Staff Sergeant David Paul Rutkowski, 24 years old. Their roles involved flexible defense and damage control. They moved when needed. They adapted when systems failed. At the rear had been Technical Sergeant Raymond Peter Romano, 26 years old. The tail gunner. His position no longer existed. This crew was not exceptional by design. They were not selected for unusual resilience or advanced engineering knowledge. They were selected because they met standards. They were trained because the war required crews faster than perfection allowed. What distinguished them was not individual brilliance. It was familiarity. They had flown together. They knew each other's voices. They understood how information flowed inside the aircraft. When Romano was lost, the remaining 8 men conducted a roll call without hesitation. Positions were confirmed. Responsibilities were reassigned. There was no discussion of heroism. There was only assessment. Each man understood his limitations. Callahan knew he could not fly the aircraft conventionally. DeLucci knew engine power, now substituted for flight controls. Mitchell recognized that fuel balance and engine health were no longer secondary concerns. Sullivan understood navigation would rely on estimation rather than precision. No one believed the situation was survivable in the long term. They did not expect rescue. They did not expect a miracle. They understood that their training had not prepared them for this scenario. What it had prepared them for was discipline, cooperation under pressure. That discipline would now be tested continuously, minute by minute, for as long as the aircraft remained in the air. At 9:58 a.m., 1 minute after the tail separated, Pennsylvania still continued descending through 27,000 feet at a steady rate of approximately 300 feet per minute. The aircraft did not enter a spin. It did not pitch sharply downward. Instead, it settled into an unstable equilibrium. The nose remained slightly low. The fuselage yawned roughly 20 degrees to the right. Vibrations traveled through the airframe as exposed structure interacted violently with the slipst REM. Inside the cockpit, Callahan tested the only control inputs still available to him. He increased power on all 4 engines simultaneously. The nose rose marginally. He reduced power. The nose dropped again. The response was slow, delayed, but consistent. Power now controlled pitch. DeLucci began adjusting individual throttles. Increasing power on the left wing engines caused the nose to swing left. Reducing power on the right wing reduced opposing yaw. The effect was imprecise, but measurable. Thrust now controlled direction. Behind them, Mitchell moved forward to assess structural damage. He unbuckled, clipped on his oxygen bottle, and stepped into the open fuselage, where the tail should have been. He saw open sky. Jagged aluminum edges vibrated in the airflow. Control cables snapped and whipped freely. There was no possibility of restoring conventional flight controls. Mitchell reported what was already evident. The tail assembly was completely gone. Romano's position no longer existed. There would be no recovery of rearward control. At 10 o'clock a.m., Pennsylvania still passed through 26,000 feet. The bomber formation was now several hundred feet above and climbing away. The distance between them increased with every second. The aircraft was alone. At this altitude, oxygen systems remained critical. Any failure would render the crew unconscious within seconds. The exposed rear fuselage increased heat loss. Interior temperatures dropped rapidly. Frost began forming along metal surfaces. At 10:02 a.m., 3 German fighters broke from pursuit of the main formation and turned back toward the crippled bomber. Their approach vectors indicated intent. A damaged aircraft falling behind was an opportunity. The fighters closed from the rear quadrant. This was normally the most heavily defended area of a B-17. Without a tail, it was undefended. Pritchard rotated his top turret aft. Castellano, extracted from the ball turret, moved to a waist position to increase coverage. Brennan and Rutkowski coordinated fields of fire. Callahan focused on maintaining attitude. Any abrupt power change risked destabilizing the aircraft. He kept engine adjustment small and deliberate. The fighters attacked in sequence. The first pass came from the right. Rear. Cannon fire struck the wing. Aluminum skin ruptured. Fuel lines were perforated. Fuel vapor streamed into the airflow. The second pass came from directly behind. Cannon shells tore through the fuselage. Radio equipment was destroyed. Hydraulic. Fluid sprayed from ruptured lines. Hydraulic pressure dropped to zero. The third fighter overshot its attack and broke away. Pennsylvania still continued descending through 25,000 feet. An engine fire warning illuminated on the panel. Number 4 engine. DeLucci activated the fire suppression system. Carbon dioxide flooded the engine nutshell. The warning light extinguished, but the engine was no longer usable. Callahan feathered the propeller to reduce drag. They were down to 3 engines. At 10:08 a.m. Callahan addressed the reality of their situation. England was no longer reachable. Allied lines were too far west. Remaining options were limited to bailing out over Germany or attempting to reach neutral territory. Sullivan calculated headings under extreme difficulty. The aircraft's yaw-made. Straight line plotting unreliable. Wind drift compounded every estimate. Switzerland lay to the southeast, approximately 290 miles away. Pennsylvania still passed through 23,000 feet at 300 feet per minute. Time was a finite resource. The Alps presented another constraint. To clear the mountain peaks, the aircraft needed to remain above 15,000 feet. Mitchell checked fuel levels. Approximately 1,200 gallons remained. Fuel consumption was elevated by constant throttle changes. Estimated endurance was 90 minutes. The margin was narrow. Callahan decided to turn south. The maneuver required careful coordination. Without rudder, the turn was achieved by differential thrust alone. Left engines increased power. Right engines reduced power. The nose began to swing. When the desired heading approached, power was rebalanced. What should have taken seconds took minutes. At 10:14 a.m. They crossed the Neckar River at approximately 21,800 feet. Below them, German flak batteries engaged with smaller caliber weapons. The shells detonated below effective altitude, but the fire was continuous inside the aircraft. Roles shifted. Hendricks moved to assist Sullivan with navigation. Mitchell monitored engines continuously. Pritchard maintained watch for fighters. Waist gunners alternated between defensive positions and damage assessment. At 10:27 a.m., Pennsylvania still descended through 18,500 feet over rising terrain. The Alps were now clearly visible ahead. Engine number 2 began running rough. Mitchell traced the issue to a partially closed fuel transfer valve, likely damaged by shrapnel. He moved into the Bombay catwalk, working without gloves in minus 35-degree air. He forced the valve open manually. The engine stabilized. At 10:41 a.m., 5 German fighters approached from the south, vectored by ground radar. Their geometry was optimal. The bomber could not evade. The attack unfolded in coordinated passes. Head-on fire tore through the nose. Cannon shells passed through the cockpit within inches of the pilots. Hydraulic systems were already gone. Instruments were destroyed. DeLucci was wounded by shrapnel, yet the aircraft remained airborne. At 10:47 a.m., over Ravensburg at approximately 14,200 feet, the fighters disengaged. The Swiss border lay ahead. German standing orders prohibited pursuit within a defined distance of neutral airspace. The danger shifted. But it did not end. Pennsylvania still continued descending towards Switzerland, flying on power, balance, and diminishing time. At 10:48 a.m., Pennsylvania Steel crossed into Swiss airspace at an altitude just above 14,000 feet. Still descending at a steady rate that could not be a steady change in airspace did not immediately change the condition of the aircraft. The bomber remained structurally compromised. Control surfaces were still absent. One engine was shut down. Another was operating outside normal parameters. Fuel continued to burn at an elevated rate. What changed was the response from the ground. Swiss anti-aircraft batteries tracked the bomber as it approached. From their perspective, an unidentified foreign military aircraft had entered neutral airspace. The standard procedure was interception or forced landing. The Swiss Air Force scrambled fighters to assess the situation. Inside Pennsylvania Steel, the crew understood the implications. They were no longer under direct German attack, but they were still not safe. Any misinterpretation by Swiss defenses could be fatal. Callahan reduced power slightly to slow the descent. The response was immediate and dangerous. The nose dropped further. Airspeed increased. Structural vibration intensified. He restored power quickly. The aircraft stabilized again. But the lesson was clear. There was no margin left. At 10:52 a.m., Swiss fighters appeared off the left wing. They maintained distance and did not open fire. Their pilots could see the damage. The missing tail was unmistakable. The exposed fuselage told its own story. Radio communication was attempted. Pennsylvania Steel's radio equipment had been destroyed. During earlier attacks, there was no way to transmit intentions or receive instructions. The Swiss fighters remained alongside, observing. At this altitude, oxygen systems were still in use. The open rear fuselage caused constant airflow through the aircraft. The temperature inside remained dangerously low. Crew members rotated positions to avoid frostbite. Hands numbed quickly. Speech slowed. Mitchell continued monitoring engines. Oil pressure on engine number 3 fluctuated. He adjusted mixture settings manually. The engine stabilized, but only temporarily. Every system was operating at the edge of tolerance. At 10:58 a.m., Sullivan identified Lake Zurich beneath scattered cloud cover. The surrounding terrain rose sharply. Mountains constrained available landing options. A controlled landing on water was impossible. The aircraft could not be ditched without elevators. A crash landing on land was equally uncertain. Callahan evaluated airfields marked on Sullivan's maps. Most were either too small or required precise approach paths. Precision was no longer possible. The aircraft passed through 12,000 feet. At this altitude, the descent rate increased slightly as air density rose. Lift characteristics changed. Engine response improved marginally, but structural stress increased. Turbulence over mountainous terrain introduced unpredictable vertical currents. At 11:03 a.m., the Swiss fighters signaled visually. They gestured toward an airfield ahead, Dubendorf. The field lay northeast of Zurich. It was one of the few locations with a runway long enough to accommodate a B-17. The approach path, however, required alignment and descent control that Pennsylvania Steel no longer possessed. Callahan adjusted power incrementally. DeLucci assisted. Despite his injury, the aircraft responded sluggishly. Each correction took seconds to manifest. Overcorrection. Risk loss of balance. At 11:07 a.m., the bomber descended through 10,000 feet. Oxygen masks were removed. The air inside remained cold, but breathable. The crew's voices became clearer. Communication improved. The runway came into view. Without elevators, flaring for landing was impossible. A conventional touchdown would result in immediate nose impact. The only viable option was to aim for a shallow descent and accept a hard landing. Callahan briefed the crew quickly. Brace positions were assigned. Loose equipment was secured. The bomb bay doors remained closed. Landing gear extension was attempted. Hydraulic pressure was gone. Mitchell manually cranked the landing gear using the emergency system. The process was slow. Each rotation required physical effort. At 11:10 a.m., the gear locked into place. The aircraft crossed the airfield boundary fence at approximately 160 miles per hour. Too fast, too steep. Callahan reduced power carefully. The nose dropped. He increased power again. The aircraft leveled slightly. There would be no second attempt. The main wheels struck first. The impact was violent. The aircraft bounced. The nose pitched downward. The forward fuselage struck the runway. Sparks erupted. Metal screamed against concrete. The aircraft slid. Engines tore free. Propellers shattered. The fuselage scraped forward, shedding components. Finally, after hundreds of yards, Pennsylvania still came to rest. Silence followed. There was no fire. Crew members assessed injuries. Several were wounded. One was dead. The rest were alive. Swiss personnel arrived within minutes. They secured the area and provided medical assistance. The crew was taken into custody as internees, in accordance with Swiss neutrality laws. From the Swiss perspective, the event was unprecedented. An aircraft had violated fundamental principles of flight and survived long enough to land. From an engineering perspective, the outcome was an anomaly. A convergence of factors: weight distribution, trim settings, wing integrity, engine redundancy. None of it was reliable. None of it was repeatable. In the hours following the crash landing at Dubendorf, Swiss military authorities began documenting the incident in detail. Their initial reports focused on security and neutrality, rather than aeronautical analysis. An armed foreign military aircraft had entered Swiss airspace, landed without clearance, and delivered a surviving crew. Procedure required internment. Medical care followed immediately after. Swiss engineers examined the wreckage. Once the crew was removed, the absence of the tail assembly was the first and most obvious feature. From an engineering standpoint, the aircraft's continued flight defied accepted aerodynamic expectations. The official Swiss assessment avoided speculation. It described the damage. It recorded impact points. It noted the unusual but observable fact that the bomber had remained airborne for more than an hour after catastrophic structural loss. American authorities received notification through diplomatic channels. For the United States Army Air Forces, the priority was the crew, not the aircraft. Survivors were listed as interned rather than missing. One crew member was confirmed killed in action. The others were alive but removed from combat operations. No immediate technical investigation followed from the American side. The war did not allow for detailed analysis of singular anomalies. Bomber losses were frequent. Aircraft were considered expendable. A survival case, even one as extreme as this, did not alter operational doctrine. Internal reports summarized the event briefly. A B-17 had lost its tail due to enemy action. The aircraft had crossed into neutral territory and crashed. Turin, crew survival was noted. No recommendations were issued. There was no revision to flight manuals. There was no change in training procedures. There was no attempt to replicate the conditions. From a doctrinal perspective, the event did not matter. It could not be planned, for it could not be relied upon. It could not be taught. The crew remained in Switzerland under internment for the duration of the war. Conditions were stable but restrictive. They were housed. They were fed. They were prohibited from returning to combat. Their aircraft was dismantled and studied only at a surface level before being scrapped. James Callahan did not give public lectures about the flight. He did not publish an account during the war. In official records, his name appears only in mission logs and personnel files. The incident itself was reduced to a paragraph. From a mechanical standpoint, later analysis by aviation historians identified several contributing factors: the timing of bomb release, the aircraft's trim settings, the structural integrity of the wings, the redundancy of four engines, the specific angle of descent. None of these factors could be guaranteed in another case. Remove any one of them and the outcome changes. From a statistical standpoint, the event remains an outlier. Thousands of bombers were lost over Europe. Many suffered severe damage. Very few survived loss of primary stabilizing surfaces. Fewer still remain controllable long enough to reach neutral territory. This did not represent a failure of physics. It represented the narrow edge where physics still applies. The aircraft did not fly in the way it was designed to fly. It obeyed forces rather than controls. Lift continued to exceed weight. Thrust substituted for surfaces. Balance replaced stability. These conditions held only briefly. That was enough. The war moved on. Schweinfurt was bombed again. Crews continued to be lost. Manuals continued to describe idealized systems, not broken ones. The survival of Pennsylvania still remained a footnote. It did not change how bombers were built. It did not change how pilots were trained. It did not change how missions were planned. What it demonstrated was limited and specific. A complex system can sometimes remain functional even after losing the components assumed to be essential. Not because it is strong, but because, for a short time, the remaining parts happened to align. When Pennsylvania still came to rest on the runway at Dubendorf, the alignment ended. Gravity, friction, and structural limits reasserted themselves. The aircraft could not be flown again. It could not be repaired. It could not be explained away. It had simply lasted long enough. That fact remained recorded, quietly, without emphasis. The manuals were not rewritten. The aircraft was gone. The crew survived. And the event passed into history, not as a lesson, but as an exception that confirmed the rules it had briefly escaped.